Hello again, everyone. Welcome to our discussion of section 4.1, where for the first time this semester we will be talking about exponential functions. One of the most important functions, if not the most important function in mathematics. Very important. So before we begin our discussion, may I remind you to please take half an hour to 45 minutes, read through the section 4.1 in your book, and then watch this video and attend the class, and then review your lecture notes and redo all the problems you saw in the book or in this video on your own without looking at the solutions, and then of course complete all the homework assignments by the due date, and then review this same material and the material before this, all the sections before this, as you go through the semester. Okay, so what is an exponential function? Well, so far, every time you saw a variable x, it was always not in the exponent of something. Right? The exponent was always a number up to this point. But if the variable you're solving for, or if the variable in a function is in the exponent of that function, then you have an exponential function. These are some examples that you see right there. Right? 5 to the x. Right? X now appears not down here with 5, so we don't have 5x, but we have 5 to the x power. So that's an exponential function. This is another exponential function, 5 to the x minus 1, or 5 to 3 minus x. In all of these functions, the variable, the independent variable x, appears in the exponent of the function, so we have an exponential function. So what are the main types of exponential function? There are two main types of exponential functions. One type is an increasing or growing exponential function. The other one is a decreasing or decaying exponential function. Basically, these exponential functions either grow very, very rapidly, or decline or decay very, very rapidly. That's a characteristic of exponential function. As a matter of fact, even in public discourse, in social discourse, in public discourse, when something is going to increase exponentially, people say, well, something is going to increase rapidly. People say, oh, that's going to grow or increase exponentially. That's what they mean. So exponential growth means very rapid growth. Exponential decay, it means a very rapid decline. So a rapid economic growth, it would be exponential economic growth. A rapid economic decline, it would be an exponential economic decline. Okay, just keep that in mind. So the graphs of exponential functions exactly behave in that way. Either they increase rapidly or decrease rapidly. For example, take a look at these graphs, right? So these two, this one and this one, the dashed one, these are increasing exponential functions. As you can see, they increase very rapidly, right? That's a steep growth of some kind. And the solid one, when I say growth, I mean increasing from left to right. Okay, not from right to left, because right to left is decreasing. No, the way we read graphs is from left to right. So it's increasing from left to right, and that graph is associated with that exponential function, y equals 3 to the x. This one is y equals 2 to the x, right? And that one is a declining or decaying exponential function. From left to right, it's dropping, right? So why this is happening? If you compare the equations of these exponential functions and their graphs, you notice that the coefficient, or the base, sorry, not the coefficient, but the base of the exponential function here and here is higher than 1. Whenever the base of the exponential function is higher than 1, you're going to have a growing or increasing exponential function. But the base of this exponential function is less than 1. To be exact, it's some number between 0 and 1. When you have a number between 0 and 1 as the base of the exponential function, then you have a decaying or decreasing exponential function. Okay? Now here, these question marks, let's read and see what they ask us to do. They're asking us to, in the graphs below, identify which one is decreasing type and which one is of increasing type. Well, you can pause the video. This is an easy exercise. Pause the video and then come back to it after I write down the answers. But this one is declining from left to right. So this is a decreasing exponential function. This line is increasing from left to right. So this is an increasing exponential function. And so is this one. This one also is increasing going from left to right, right? So this is also increasing. Okay. Right below this graph, we have a bunch of other graphs, and they want us to also identify which one is increasing or decreasing. I highly encourage you to first pause the video and then come back to it in 20 seconds to see, after you've written down your own answers, to see what my answers are. So for graph A, I'm assuming you've already done that, and now you're back. So for graph A, it's increasing, right, from left to right. So this is increasing. This one, from left to right, it is declining. So this is a decreasing exponential function. This one, it's increasing from left to right. It's increasing. This one, it's declining or decreasing going from left to right. And this one also, it is declining from left to right, right? So decreasing once again. Okay. In this section of your textbook, they talk about applications of exponential function to business context. And I think that's very smart, because that's most common applications of it these days. But of course, exponential functions have applications, a lot of applications in science, in nature, in terms of the growth of the bacteria, growth of cells, or declining or decreasing the number of cells. If the cells are going away or are dying, then that death of cells could be exponential decay. Nuclear material, plutonium or uranium, have exponential decay over time. Of course, that time is very long, but their decay factor is exponential, and it's exponential decay or declining over time. So in nature and science, you do have applications, but your book decides to focus on business applications, which is just fine. So in business applications, we have either a simple interest, either a simple interest rate, or a compound interest rate. Okay? In the simple, so what's the difference between simple interest rate and compound interest rate, right? So here we talk about simple interest. This is talking about compound interest. What's the main difference between those two? Well, the simple interest, if you open an account, let's exaggerate to make a point. Suppose you open an account with $1,000, and suppose this account has 50% interest rate, right? Again, let's exaggerate just to make a point. So that means after, and suppose you want to invest this money in this simple interest account for the next 30 years at 50% interest rate, right? If it's a simple interest rate, then for the next 30 years, only the principal of your money, only the $1,000 will earn that 50% interest. So at the end of 1 year, you will have $500 interest, right? At the end of now your account has $1,500 in it, and if you don't touch the money, that $1,500 is there, but only the $1,000 that you originally invested is going to earn simple interest. That's why we call it simple interest, because that 50% interest rate only applies to the principal that you invested, but never to the accumulating interest that is there in the account. So the second year, the 50% is going to apply to $1,000, not to $1,500. And in the third year, it's going to apply to not to $2,000, but to the original $1,000. Okay? But the compound interest is an interest type that is going to apply to everything that is in the account. Not only the principal, but also whatever interest that is being accumulated in the account is going to then earn interest on it. Okay? So if that $1,000 money that you invested in the account, if that 50% interest rate was a compound interest rate, then in the second year, the 50% interest year would apply to $1,500, and so on. And in the third year, again, to whatever you have in the account accumulated, and you didn't touch that money, the totality of that money, everything mixed, the principal, the accumulating interest, will earn that 50% interest in the subsequent years. Okay, so I hope the difference between simple interest rate and compound interest rate is clear. So having said that, then, and you should read these things that I've written down in the worksheet, because I've summarized what I've said right there in this very brief paragraph right there. Okay, so we have an example here. It says suppose $1,500 is invested and earns 6.5% simple interest rate annually. How much will there be in the account after 8 years? Now remember that 6.5% will only apply to the $1,500 originally invested and never to anything else. So we need to find out how much interest that is. So first let's calculate 1,500. And I encourage you to answer this question, pause the video, answer this question, and then come back to it after you have completed your own solution. So I'm assuming you've done that, and now you're back. So $1,500 times 6.5%, that would be 0.065 converted to decimal. When we calculate these numbers, we need to convert from percentage to decimal. Remember, percentage is usually used for reporting something, not for calculating. Sometimes, it's very rare, but there are some formulas where the formula accepts the value as a percentage, but not here. So we convert to decimal. 6.5% is 0.065 times 1,500. So I'm going to need my calculator here. All right, so let me clear what's on there already. So 0.065 times 1,500, and it's $97.5, right? So it'll be $97.50, right? So that interest, because this is a simple interest account, isn't going to change over the 8 years. It's going to stay constant. So we have 8 times 97.5. Let's see what that money is. So 97.5 times 8, that's $780. Now that's the money that accumulated in the account in addition to the $1,500 the amount of money that was invested originally. So they're asking how much will there be in the account after 8 years. So it'll be the money in the account after 8 years, it'll be $1,500 original money plus the accumulated interest of $780. So it'll be $1,500 plus $780. All right, so let's do that. Let's add that to $1,500. So $2,280. Like that. Okay. So the compound interest, I don't think we have in this section. Your book talks about your book doesn't talk about continuous compounding. They only talk about the periodic compounding, which is this formula. So this is the compound interest calculation. You can call it that, or also known as periodic compounding. So because it's a compound interest calculation, this money that you invested in such an account will accumulate interest on everything, on the principal as well as the interest. Okay, so the formula is that we have to understand all the variables involved here. So the AT, I'm surprised I didn't define it here. So this AT, let me define it, is the future value that we're calculating. Suppose you invest, say, $2,000 now in 10 years in this compound interest account, and in 10 years, how much is there in the account, or will there be in the account? The AT is that future amount that we're calculating. The lowercase p is the principal amount. That's that. 1 is always 1, plus R is the annual interest rate converted to decimal form, never in percentage form, guys. I've seen many people on exams, they use percentage form. No, you have to convert it to decimal form. So R is the annual interest rate converted to decimal form, divided by N. So what is N? N is the various compounding periods that we may have in a year with this compound interest calculation. So if N, and we'll get to other variables. So if interest is compounded annually, that means once a year, then N equals 1. If interest is compounded semi-annually, that means twice a year, every 6 months, then N equals 2. If interest is compounded quarterly, that means every 3 months, right? So N equals 4 in that formula. If interest is compounded monthly, that's 12 times per year, so n equals 12. If interest is compounded daily, n is equals to 360. My business colleagues tell me that in business calculations, for daily compounding of interest, they use 360, not 365. So if you're curious why that is, please ask your business faculty. They know. I just know that's what they do, but the more in-depth reason behind it, they would know and they could tell you about it. But so it's not. What's important for me that you understand at this point is that we're not going to use 365 for annual compounding of for daily compounding of interest. We're not going to use 365. We're going to use 360. We're going to stick to the proper business practice, okay, which is n equals 360 when we have daily compounding of interest. Now T is the number of years an amount was invested. So if the money was invested for 15 years, then T would be 15. And N appears, take a careful look, N appears as the denominator of the interest rate converted to decimal, as well as in the exponent, times T. Okay, very, very important. All right, so now that we've covered that, let's take a look at an example of this type. So suppose $500 is invested at an interest rate at 3.75% per year. Find the value of the investment after 16 years. So right there we have, as we read, let's identify the different variables here that we have. Suppose $500 is invested, right? And by the way, let me write down the formula here. Maybe I'll write it on top here, that AT is equal to P times 1 plus R over N to N times T exponent. Remember that? So that's our compound interest formula. Now in that formula, $500 would represent the principal, right? The P, at an interest rate of 3.7% per year. So R would be 0.0375. Find the value of the investment, that's AT. So this piece, they're asking for A, or that piece, after 16 years. So that 16 is T. What about N? Well, for N, we have three cases. Case A, case B, and then case C. When we get to it, you'll see that as well. Okay? But for N, we have to see what case we have. So the interest is compounded semi-annually. So semi-annually, that means N is equal to, do you remember what it's equal to? It equals to, if interest is compounded semi-annually, N equals 2. Okay? So we have everything we need to answer that question. For these, please pause the video and run through this calculation on your own and then come back to the video. Here, part A is asking for the future value A if interest is compounded semi-annually. Part B is asking for the future value is if the interest is compounded quarterly. And for part C, the problem is asking for the future value if the interest is compounded daily. So please pause the video, carry out your calculations for each case, and then come back to the video. Okay, I hope you've done that, and now you're ready with your solutions completed, and you're ready to compare your solutions with the ones I'm going to write down. Okay, so If the interest rate is compounded semi-annually, then we can easily calculate that future value. So A is equal to $500, which is the principal, times 1 plus R, which is 0.0375, divided by N, in this case semi-annual, so N is 2. The power would be N times T, or that T is 16 years, right? And N is 2, so 2 times 16. Okay? So, one of the things that you should know also about this is when you calculate this formula, try avoiding putting everything in your calculator all at once. Avoid that. Because a lot of times I've seen people do that and make an error and get a wrong answer because they forget where to put the parentheses, where to put the parentheses for the exponents. They make error in inputting the information. Not that they don't know what they're doing, they do. But if they do this calculation in steps, they're going to avoid making an error. So calculate this quantity in pieces rather than all at once is what I'm saying. So I'm going to do that myself. So $500, I'm not going to touch that for now. I'm going to start from inside the parentheses. We have 0.0375, right? 0.3. I'm going to divide 0.0375 by 2 and add the result to 1. So 0.0375 divided by 2, look at that quantity, and now I'm going to add 1 to that, plus 1, right? 1.01875. I'm going to write that down. 1.01875 raised to 2 times 16, right? It should be 32, right? 2 times 16, 32. So I'm going to put the 32 here. Now, I'm going to raise this number inside the parentheses to that power and multiply back by 500. So the 500, even though it comes first in the formula, it is the last thing I incorporate in my calculator. Okay, so multiplying by 500 is the last thing I do because I have to observe the order of operations here. So let's bring this back. I'm going to raise that quantity to 32 power. So 1.01875 raised to 32 power. So we get that, 1.8120237. So let me tell you, when you're working with exponential values, exponential formulas, exponential functions, in the middle of your calculations, always keep as many, at least, well, I shouldn't say as many, but at least 4 decimal places. So here you should keep, at the end you can always round numbers, but in the middle of your calculations, you want to keep at least 4 decimal places. So you should keep at least up to 0, okay, if not more. Because the reason is, when you work with exponential functions and values, if you round too early, if you round, let's say 1.8, if you don't keep 1, 2, and so on, if you round too early too much, the final answer will be off by a large amount. I shouldn't say large amount, but certainly by a significant amount. So to avoid that, to stay as close as possible to the real value that you're calculating, in the middle of your calculations, keep at least 4 decimal places, if not more. So I'm going to keep 1.81202. I'm going to keep up till that 2 right after 0. Okay, so this will be 500 times 1.81202. Now I'm happy. Now, even if I'm off from the real value, it'll be by a very, very small and even negligible amount. So you definitely want to do that. Okay, now I'm ready to multiply by 500. So, but in my calculator, since the number is already there with its full, with all the numbers included, I don't mind that either. I'm just going to multiply that by 500, and I'll get, because this is talking about dollars and cents now, this is my final answer. So I can round that to 2 decimal places because it's talking about money. So $906.01. $0.01. Okay. So there. Okay, so I hope this matches your own calculations. And I hope you've done this for part B and C as well. Okay, so this for part B, the interest, which was that 0.0375, that 0.0375, so that's R. And T is 16, we know that. The principal money didn't change, it's still $500. We're still looking for the future value A, that's the question mark. But the N is something that is changing, right? So all of these stayed the same, but the compounding period didn't stay the same, right? The compounding period changed from semi-annual, which was part A, to quarterly. Quarterly, that means every 3 months or 4 times per year. So N, do you remember what N was for quarterly compounding of interest? N, if interest is compounded quarterly, N equals 4 times per year, right? 4. Okay, so once again, we're going to plug in that formula, right? Let me write the formula here so it's in front of us. A equals P times 1 plus R over N to N times T power, right? That's the formula. Okay, so now we're solving for A, or the future value. P stayed the same, $500 times 1 plus 0.0375 divided by N. We're dealing with compounded quarterly, interest compounded quarterly, so N equals 4. And then again, N up here is equal to 4 times 16, which didn't change, right? The time over which we're calculating this amount didn't change. Okay, so once again, we have to observe the order of operations. So 500 stays where it is. Let's divide 0.0375 by 4 and add 1 to it. Okay. So let's see where I can put this so you can see it better. Well, maybe this way. That's better, right? Okay. So 0.0375 divided by 4, it's that, plus 1, okay? 1.009375. So in this case, because I have 2 zeros before 9375, I'm going to keep all of that. So I'm going to write 1.009375. Okay? And then the power, 4 times 16, which should be 64, right? 64 We'll put it here. Now, before we arrive at the final answer, what do you think about this result? Do you think this will be higher than that or less than that? What do you think? Well, if you said it's going to be higher, you're absolutely right. Because when compounding of interest happens faster or more frequently, or I think that's the better word for it, more frequently per year. Because in part A, that was happening twice a year, now it's happening 4 times. And in part C, it's happening daily, so even more frequently. When that happens, the money is accumulating faster because it's accumulating that interest at a faster rate. Okay, so we expect this amount to be higher than $906. Not by much, because the original investment was small. It was only $500. Nonetheless, this amount is going to be higher than what we had in part A. Okay, so now I'm going to raise this quantity to 64 power. All right, so we have 1.009375. Raise that to 64 power. What do we get? We get 1.8170. So I'm going to keep these numbers all the way to the first 3. So this is equal to 500 times 1.81703. But of course, my calculator makes it easy because it already has all the numbers. But on paper, I'll write at least 4 decimal places. In this case, I have 5 decimal places. And multiply that quantity by 500. So now we have $908, and let's round that to 52 cents. All right? So a little over $2 more than what we had in part A, right? But that's okay because the original investment wasn't that large. Okay, so for part C, the compounding happens daily, right? But nothing else changes. So the interest rate stayed the same, 0.0375 or 3.75%. The time didn't change. It's 16, or T is 16 years still. The original investment didn't change. It's still $500. And we're still looking for the future value. But in this case, interest is being compounded daily. So if I bring back this list, if interest is compounded daily, N, we have to use 360. So N in this case is 360. Okay. All right, so the formula, once again, let's keep it in front of us. It's future value equals P times 1 plus R over N to N times T power. Okay, so let's plug in. For P, we still have $500. 1 plus 0.0375 divided by N, which is 360. Then in the power we have 360 times 16, which is the number of years over which this money is invested. Okay, so let's observe the order of operations. We have 500. Let's divide 0.0375 by 360 and add to 1. Okay, so we have 0.0375. Yes, that's correct. 0.0375 divided by 360. That very small quantity, right? Plus 1, right there. So I'm going to keep everything all the way to 1.7. I'm going to keep everything here because of these 3 zeros, so those become more important actually. So 1.000104167 raised to what power? 360 times 16, right? So let's calculate that. So what is that quantity, 360 times? 360 times 16, we have 5,760, right, as the power. So 5,760. Okay, so the next step is for us to figure this quantity raised to that power. Let's do that. Okay, we have, okay, so all of that 1.000104167, raise that to 5,760, we get that quantity. So I'm going to keep everything all the way on paper at least. So 1.8220, I'm going to round that 6 to 7. But now I can just keep that and multiply it back by 500, right? So times 500, which makes my number, my final number, even more exact. So $911.03, right? 3 cents. So here we have a scenario where as the compounding of interest changed and became more frequent during the year, the money was growing with it as well. The accumulated money was growing as well. 906 to 908 and 911 at the very, for a daily compounding of interest. Okay, please remember to read through your book for the next section that is coming up in the next video. And thank you for persisting through this video again, and for watching the video, for attending the class. And I'll see you all again next time.